Hello everyone, and welcome back to The Hidden Truths, a place where we explore scenarios, histories, and truths hidden from public view. Big thanks to Cirnosad for compiling this. Improving the nuclear bomb, scaling up, and fusion weaponization. In this episode, we're going to learn about the process by which Gadget and Fat Man were turned into efficient, compact, and more practical nuclear bombs with way more yield. And later still, the super bomb, which uses fusion. Fat Man was a large 3.5 meter by 1.5 meter, 4.7 ton bomb with only a 15 kiloton yield. Generals wanted nukes which were cheaper, less heavy, and more powerful, because fission materials were expensive and took a lot of time to enrich. The weight was a factor because they wanted to deliver more of them, and they wanted them to be more powerful because it was fashionable to threaten cities at the time. Fat Man's implosion design used a 32-point high explosive lens. It made use of 6.2 kilogram phase plutonium gallium pit for practical reasons. Note this is below the actual critical mass at standard temperature of 10 kilograms, but will still go supercritical for 3 reasons. The shaped charge will compress the pit dramatically, causing the plutonium atoms to close in spacing. Plutonium has an A-phase allotrope that is about 25% denser. Phase transition during detonation, a surprising bonus. And increasing neutron flux via reflectors, basically a tamper. For number 3, the pit was placed in a tamper made of uranium-238, which is depleted uranium, coated with beryllium-doped plastic, which reflected neutrons. All in all, only 16% of the plutonium fissioned, but the depleted uranium was also underwent fission, when exposed to energetic neutrons, accounting for 30% of the yield. The components were part of the physics passage and accounted for a small percentage of the bomb's weight. The majority of the mass was in the high explosives and the bomb casing. Recall from Physics 1 that the latter is needed to hold the bomb together until the reaction is complete. I'll let you look at the cross-section. There was a room for improvement. The pit was a solid sphere, and this wasn't ideal. If it were a hollowed-out sphere, the compression wave would crush it inwards into a neutron source initiator with huge deformation. This has a highly nonlinear advantage in criticality. The hollow sphere design also self-tampered, meaning the deformation formed a neutron reflector out of the plutonium itself, and a highly supercritical region in the center. So this required more precise shaped charge. It required less explosives and a lighter casing. Another improvement was the levitated pit, essentially allowing an air gap to exist between the tamper and the pit. This created a shockwave that increased the compression even more, resulting in twice the yield. The photo is for illustrative purposes only. A code was said to be used. The initiator, usually polonium, could be replaced with a pulse neutron emitter to avoid pre-detonation, which would reduce the yield. Eventually, this would be integrated into a chip. Finally, a more precise 92-point shaped charge would enable the use of the hollow pit. These improvements let the two pass. Highly efficient bombs, such as the Mark V, with yields up to 120 kilotons, burning up most of the plutonium-uranium pit, and making good use of the tamper while only weighing 1.2 tons. In light bombs, the Mark XII weighed 540 kilograms with a yield of 14 kilotons. Remember, the Fat Man was 4.7 tons. But for some, 120 kilotons, almost 6 times of Nagasaki, wasn't enough. The Mk-18 achieved a yield of 500 kilotons. It was quite similar to the Mark V design, but employed a unsafe 60 kilogram highly enriched uranium pit, which had aluminum boron reflectors inserted to stop it from pre-detonating on its own. This was of course a dead end, as there's no way to scale the design further due to safety concerns. These reflectors were removed at the last step of arming, but that didn't stop the UK from doing something almost equally insane. Orange Herald had a yield of 720 kilotons. Orange Herald wasted 117 kilograms of highly enriched uranium, almost the annual production of the UK at the time, and used a hollow pit with a special material inside. The material did not operate as expected, and the device was considered a failure. Fission-based nukes seemed to reach the end of the line here. You could not improve upon them without waiting for better materials and electronics. But for one mad scientist, these bombs were merely a stepping stone for something better. The super bomb, aka a fusion bomb. But before we can cover what super was meant to and what came of it, we need to revise 3 subjects: thermodynamics, atomic physics from the Coulomb law perspective, and open questions regarding the structure of atoms and subatomic particles, and nuclear fission. Since nuclear fission bases were largely optimized through a number of ingenious geometrical techniques, including hollowing out the pit to increase the explosive impact, compression, levitating it, and more. Since we have hit a limit just under 1 megaton, to reach the upper limit, some dangerous and impractical steps had to be taken, using 4 times the critical mass, dividing with boron sheets up until the weapon is armed. One man found these engineering feats boring and inevitable: Edward Teller. To Teller, the atomic bomb was simply the stepping stone to his real interest, a multiple-stage, fusion-based weapon he called a super bomb. It operated in a very large, different manner, and instead of splitting atoms, the bomb will also be fusing some deuterium and tritium together. Nuclear fusion is a phenomenon that was first postulated well before fission. It was first demonstrated by Lord Rutherford, who fused deuterium into helium by utilizing 400,000 volts to overcome the positively charged field of the atom, creating a heavier atom and ejecting a neutron and energy. A very important aside for later, you can use Coulomb's law to estimate the minimum energy required to overcome the electrical field of the nucleus of a deuterium atom using another deuterium atom and obtain the required voltage of 721,000 volts, well above what Rutherford used. To make some simplification assumptions, it ignores the presence of an electron, which would attract the incoming deuterium rather than repel it, assumes the atoms must make perfect contact, and assumes our measurements or conceptualization of a proton-neutron radius is correct. The last point is the Achilles heel, as measuring the proton's radius has resulted in different measurements based on what kind of experiment was conducted. No experiment has successfully measured a neutron's radius. This enters the realm of particle physics, and we'll cover it later. The problem with fusion in comparison to using the chain reaction idea in fission is most of the energy emitted by the reaction is transmitted as 17 millielectron volts kinetic energy in the motion of the neutron and the resultant product helium. It doesn't just emit gamma rays like fission. As we demonstrate in the first thread, the fission reaction of uranium-235 liberates something around 170 millielectron volts of energy in the form of gamma rays, but requires a slow neutron. Recall that the cross-section is also highly nonlinear and contains resonance. It may seem like the fission reaction generates more energy, and on a per-atom basis, you would be correct. By weight and density, the fusion reaction generates far more energy, 5 times the amount, just not in the most convenient form, gamma rays, i.e. photons. Worse yet, these reactions, just like the Rutherford experiment, seemingly require a lot of energy to speed up the atoms to the point where they will fuse. Once this energy is available, though, the reaction is self-sustaining, as the energy liberated will result in collisions. The reader with the keenest eye will realize that the neutrons liberated by the reaction can be used to make the fission material undergo fusion. The neutrons will have the most energy, and so would not be ideal for uranium-235, which requires slow thermal neutrons for fission. But as you can see, uranium-238 drastically increases its cross-section and becomes as fissile as uranium-233 uranium-235, and plutonium-239 for fast neutrons. Uranium-238 is cheap and can be part of a bomb's tamper, meaning its fission can be boosted. The US was first to put weaponized fusion to the test in the most crude manner during Operation Greenhouse. A device called the IDA, an amount of cryogenically cooled deuterium and tritium was injected into the hollow core's pit cavity. It needed to be liquid to maximize density. The pit itself was made of highly enriched uranium. The amount of additional energy released by IA fusion was estimated to be only 1% of the total released. But having so many free neutrons generated through this boosting was said to contribute the doubling of the yield via subsequent fission, 45 kilotons overall. The cryogenic freezing requirement made the bomb impractical for deployment. Furthermore, this was just the most crude use of fusion, simply to generate more neutrons for pre-existing nuclear components to react with. This was great for the miniaturization of nuclear bombs, however. This came at a cost. The fallout from fast neutron fission of U-238 was measured to be significantly higher than the slow neutron, highly enriched uranium fission. Nevertheless, the US had bigger plans, and in 1952, the cryogenic deuterium tritium for its next and most significant nuclear bomb test, Ivy Mike. Ivy Mike wasn't just a really big nuclear bomb per se, it was a nuclear building, weighing 80 tons. Apparently this fact was severely mocked in the Soviet Union. There was no way to deliver this kind of weapon. Cryogenic equivalent aside, it produced a record yield of 10.4 megatons. The design did not merely use boosting, but also used a second stage consisting of another fusion fissile fuel, with a geometry that allowed for almost arbitrarily increases in yield, a cylindrical one. This was called the Teller-Ulam design. We will discuss this at another time. The Russians were quickly catching up, though, through and, in some sense, exceeded the Americans in 1953 RDS-6S. This actually used an older idea by Teller, which is called the layer cake design. Alternating layers of fission and fusion stages would be compressed by the explosive lens. The key difference to this design is the use of a different kind of fusion fuel, solid lithium deuteride. The Russians had beaten the Americans to the punch, as an insufficient amount of lithium-6 was stockpiled by the US, while the Russians had plenty to use for the bomb. While lithium deuteride is cold pressed, can be machined using standard techniques with great precision. This allowed for the use of any geometry. Furthermore, lithium-6 readily undergoes fission, producing the tritium atoms with a total of 4.8 million electron volts of energy. This then fuses with the deuterium inside. Lithium-6 is a rare isotope of lithium, the most common one being lithium-7, which is projected to make up more than 92% of Earth's reserves. Coincidentally, lithium-7 can also undergo fission if a fast enough neutron collides with it. This later results in tragedy. But that's all for Physics 4, giving you an introduction to fusion, energetic neutrons, and creating fast-moving particles in more neutrons, and so on. Amazing synergy. But next time, we will tackle thermodynamics and multi-stage nuclear bomb design. I hope you all enjoyed watching. Bye-bye!